This is Anthony Wise, Mathematical Logic 5154. This is my final presentation. We're going to do two parts, parts 1 and part 2. This is part 1. So we'll be talking about decision matrices. In 1981, Stuart Pugh invented the idea of taking a complex decision and breaking it down into quantifiable scores so that each decision variant could be numerically ranked. This is of interest specifically in the design phase of engineering due to the large number of unknown and possible decision variants. And the goal for this is to remove any bias from the process, but still maintain this expertise. So specifically for teams or artificial intelligence, you want to remove any personal bias from the decisions itself or the options itself, and you want to retain all of the skill, craftsmanship, whatever type of expertise that you're working with. You want to retain all of that per each option that you're trying to select. So basically, this is just my little graphic to go through that. You have all of these decisions. And all of these are options basically for each decision variant, so you have a base decision and then a variant of that decision. And then all of these options come into play. So this decision matrix is basically a way to take all this scattered group of options, kind of organize them into some kind of matrix, and so that it outputs you the decision variant that is going to be best suited based upon your optimization criteria. So this is in real life. This is kind of what this looks like. So I basically said, for an example, let's build a motorcycle. And so a motorcycle has two wheels, but it can have any number of options for frame, for tank, seat, lights, handlebars. I mean, you name it, and there's a choice to be made there. And so I made this graphic right here. This is generically what we want. We want a motorcycle, right? But each one of these is a variant of what that actually is. So if you think about it, this would be your decision space D, and then each one of these is a sub DI variant, so this would be like DJ, K, right? All of these fit the profile of being a motorcycle, but they don't necessarily, to get to each one of these options, you have to, or each one of these outcomes or decision variants, you have to be able to work through a group of options and weight them, and then decide, oh, okay, this is what I want it to be like. So that's my real world. And all of these motorcycles, I've had a hand in building, so it's kind of neat. So what does a decision matrix look like? So just to get started off really simple, this is for a non-weighted decision. Note that this set of variables or options, right, basically goes straight into a score, a subscore, and then those get summed down to this main score S right here for each decision variant. Okay, so here's your decision space, right? And then each one of these, car 1, 2, 3, 4, 5, and 6, are your possible DIs, right? This is your subscores, and this is your overall score. So then you would look at this subscore space for an optimum criteria, which is what I'm calling a set A, right? So then the difference between that and a weighted decision is that you have, here's your list of options, right? And then you have this additional weight. And this weight is basically you saying that I have a preference for each one of these on a scale of 1 to 10, but not exclusively 1 through 10. There are multiple numbers, so like 9, 9, 9, right? It's just how much you want that. And so this is the overall weight of each one of these. This is really what I want. I really want to be, cost is really important to me. Color is really important to me. And then the type of car is really important to me. The location of where it's at, I can get it shipped, doesn't really matter. The engine, they're all going to have kind of the same engines, that's not really that big of a difference. The electronics package, I don't care if it's got a fancy radio, whatever, right? So those are all your weights for your decision space as a whole D. But then what happens is you go through and decide what your score is for your options or your variable V, and then these two scores 9 and 2, right? They get multiplied over. So if you just draw a line through that, they get multiplied over to your score S here. And then these get summed down just like in the matrix above to an overall score of S. This is going to be sub DI because it is a part of this decision variant. And then all of those are listed here. And then just like above, your optimization criteria is going to affect what scores you see here. So if you're looking for a maximum, obviously it's this one, which would be car 4, right? If you're looking for a minimum, then it's going to be this one, and it's going to be car 5. So in this decision, we actually denoted that we wanted a maximum value, so this is what we would go with. So that's kind of an overview of what it looks like and kind of a real brief how it works. So then the next is the process map of moving through the detailed steps of each one of these to get to the end decision, right? You start off with what I'm calling a forcing function f, and we'll define all of these variables formally in part 2, but this kind of gives you some kind of tactical feel about what they do and where they're supposed to be. So forcing function f, right? The forcing function I'm deeming as this is your team, right? Or this is your artificial intelligence. This is basically what's driving you to make the decision. This is telling you that we need a decision. That's the part of that, right? So that this is your system input. Your system is saying, I need a decision. So it opens a decision space D. So there's your decision space D. And then so for each one of, for each decision, there's a possible variant. So I want a car. Well, is that a Toyota Camry, or is that a Camaro, or is it a Corvette, or is it a sedan, or is it a coupe, is it a hatchback? Even types. So that's what these decision variants are right here. It's the different sub decisions that are within this, and this is what you're trying to optimize, is which one of these within an overall decision structure am I trying to get, is going to be the best one based upon an optimization criteria. So each one of these decision variants, basically you get an option set and you get a weight, and this is for both non-weighted and weighted. And I know what you're thinking, I'm specifying a weight, but you're saying that my decision matrix is a non-weighted matrix. This is really easy to think about. You're just generalizing it out. Your weight for a non-weighted matrix is 1. So you multiply it by 1 and nothing changes. So that's what I'm saying there. So this holds for both weighted and non-weighted. So you get this package, right? You have a decision variant. It comes with a weighted pair of options and weights, right? And then that for each package, right, each decision variant, right, goes into this, what I'm calling the score or scoring function, phi. And the scoring function basically takes these two things and gives you a subscore, right, for your decision variant. So there could be 10 options, like in the last slide we saw that each car had, like, I think 12 options. So each one of those options for the data pair, for the weight and for the options, gives you a sub-score. So because there are multiple options, you're going to get scores, plural, right? Mini scores. And those scores are going to be in the column of your decision variant. So then what you're doing in this step right here is summing those scores down to an overall score, which is, this is your overall score, so large S, right, sub DI. Your DI represents your decision variant that it goes to, so 1 to 1, right? And then basically from that subscore here, you're throwing your set of all subscores into, or your set of all overall scores, right, over into your optimization conditions, which is a set A. And that can be like, I want the top 3. I want the minimum. I want the maximum. I want 75% of what the top score is. Whatever that condition criteria is that you're using there is what you're using to filter, to use our math logic term, to filter your data, right? To get only one, or in the case if you wanted a top, your top 3 decisions or bottom 3 decisions, 3 decisions. But typically what we'll be looking at is 1 decision. You want 1 decision out of the backside. That's what we'll be considering in this set. So that's the process. So that basically takes you from your forcing function all the way through your process to what your decision variant is that you actually decided on. That's the one you're going to get. For the car, you looked at 6 cars, you had 12 options, you got all those subscores, you got all the overall scores for each decision or each car variant, right? Car 1, 2, 3, 4, 5, 6. You put it through your optimization conditions, and then you get your decision for which one you're going to buy at the end, right? So how is the decision matrix constructed? I have 2 slides for this, so we're going to go through these really quick. For non-weighted, this one's non-weighted. There's no weighted column here, right? Like I said, this decision, right, what car to buy is your decision space D. And then each variant, 1, 2, 3, 4, 5, 6, is your DIs. And then here is your options set. And so from your options set through your decision variants, right, that goes into your scoring function, and then that's how you get your subscores, and those are labeled or indexed, right, to use a math term, indexed with inside your matrix for columns N and rows M. Columns M and a row N, right? So here's your subscore for each option, and it has a position marker within the matrix. That allows you to align your subscores within your DIs or decision variants so that when you go and sum all down through your columns, you're actually summing the scores that apply directly to the scoring criteria that you have developed for option 1 and decision variant 1. You're not summing scores that don't have anything to do with your variance. You're not summing scores from 3 in decision 4 because that wouldn't really get you anything that you needed, right? And then the last one, like I talked about, is you're taking this set right here and you're looking for your optimization set A, and what that means. For this, we're looking for a maximum value. So here's your maximum value. And then if you'll notice, if you're really, really paying attention, right, then this score right here and this score right here are the same score. So then how do you decide? So we'll cover that situation towards the end of part 2 of 2. So, okay. So here's your weighted matrix. So the difference with this one is that you actually have a weight column. So everything is still the same. You have your decision space, you have your DIs, you have your option set, right? But instead of just having an option set and then scoring those options, you also have a weight that you apply to your whole decision space. So then basically what happens is you go from your weights to your options to your decision variant, and then that goes over here to your scoring function, phi. And from your scoring function phi, you're going to get a subscore, right? And those subscores are going to be labeled with positions M and N within your matrix, and that's where you're going to get those, right? So, and then from there, you get this sum, right? You sum down, just like the arrow says, and you get your overall score, and then you push that overall score through your optimization criteria. And like the other one, the maximum value is what we're looking for your optimization, so then that's going to be your 612 right there for this variant. So you've pushed it through your optimization criteria. So you retrieve this score as the maximum value. So now you're looking for your DI variant. So maybe car 4 is going to be the one that you buy, right? All right, so that's the end of part 1. We're about to move on to part 2. We'll break here so the video sizes are about the same. Please post any questions you have in the discussion forum and tag any of the slide numbers or part 1 or part 2. I'll figure it out. So thanks for watching.